looking at right now is openly defying the laws of physics. When a fighter pilot pulls a 9G maneuver in the sky, the load placed on the aircraft reaches absolutely mind-bending proportions. The aerodynamic force slamming into these wings is roughly 50 tons. That is the equivalent of hanging 4 fully loaded double-decker buses from this paper-thin wing structure. Under normal circumstances, this aircraft should tear apart like wet paper, its pieces scattering across the sky. Under extreme pressure and dynamic loading, metals bend, buckle, and eventually, they surrender. But these jets don't surrender. How? What secrets lie beneath that sleek skin, pushing the absolute limits of physics and material science? Today, we are looking at one of aviation's darkest secrets: why fighter jets don't rip apart in midair. And by the end of this video, when you see how a single connection point holds this entire billion-dollar system together, you will never look at an airplane wing the same way again. To understand the impossible durability of modern fighter jets, we first need to meet engineering's most insidious enemy: metal fatigue. Take the de Havilland Comet, history's first jet airliner. In the 1950s, it was supposed to rule the skies. Instead, the plane started disintegrating in midair for no apparent reason. The culprit? The windows. The Comet had square windows. In mechanical engineering, we call this stress concentration. In a pressurized fuselage, force accumulates violently at sharp corners. With every single flight, with every pressurization cycle, microscopic cracks began to form at those corners. Think of bending a paperclip back and forth until it snaps. That is metal fatigue. When materials are subjected to constantly changing dynamic loads, they tear at a microscopic level over time, even if the force is well below their yield strength. And fighter jets don't just fly. They're trapped in an endless cycle of flexing, twisting, and snapping back. During a dogfight, the airframe morphs so much that the jet acts like a giant flexing metal muscle. We used to build airplanes by riveting thousands of small aluminum pieces together. In the 1988 Aloha Airlines disaster, metal fatigue accumulating around thousands of tiny rivet holes caused the entire roof of the aircraft to peel off in midair. Every single rivet hole is a weak point in structural integrity. It is an open invitation for a crack to start. The solution is called monolithic machining. Modern aerospace engineers no longer build critical skeletal frames by bolting hundreds of small parts together. Instead, they take a massive, solid block of metal, weighing hundreds of pounds, place it into an advanced 5-axis CNC machine, and shave it down until only a single seamless component remains. No joints, no rivets, no weak points, just continuous fluid load transfer. And these blocks aren't made of ordinary metal. Enter the holy grail of material science: titanium alloys, specifically Ti6 Al4V. Why not steel or just aluminum? Because when a fighter jet hits Mach 2, twice the speed of sound, air friction alone heats the outer skin to a blistering 200 to 300 degrees Celsius. At those temperatures, aluminum rapidly loses its structural strength. Steel? Steel is way too heavy. Use it and your jet becomes a flying brick. Titanium, however, is as strong as steel, but nearly as light as aluminum. More importantly, it has an incredible resistance to heat and a phenomenal fatigue limit. It is nature's ultimate shield against that terrifying metal fatigue. But the perfect material is only the first piece of the puzzle. There is a strange paradox in engineering. If you make a structure too stiff, too rigid, you practically guarantee it will shatter under the first major impact. You know how skyscrapers in Japan are designed to sway like trees during an earthquake so they don't collapse. Fighter jets do the exact same thing. We call this aeroelasticity. When a jet enters a 9G maneuver, the tips of those massive titanium and composite wings bend upwards by several feet. If they didn't flex, an unimaginable amount of stress would accumulate at the wing root, where it meets the fuselage and the wing would simply snap off in seconds. What gives the wings this perfect flexibility are carbon fiber reinforced polymer composites. When engineers manufacture these composites, they calculate the exact orientation of the microscopic fiber strands. Because of this, as the wing bends upward, it also twists slightly on its own axis. This smart twist actually changes the wing's angle of attack, instantly shedding excess aerodynamic load and relieving the aircraft. The machine actively morphs in midair to save its own life. What gives the wings this perfect flexibility are carbon fiber reinforced polymer composites. When engineers manufacture these composites, they calculate the exact orientation of the microscopic fiber strands. Because of this, as the wing bends upward, it also twists slightly on its own axis. This smart twist actually changes the wing's angle of attack, instantly shedding excess aerodynamic load and relieving the aircraft. The machine actively morphs in midair to save its own life. Now let's look at the most terrifying aspect of this flawless system. In aviation literature, there is a term called the single point of failure. Certain components are so critical that they simply have no backups. Think about the jet engine generating the massive thrust of an F-16 or an F-35. This screaming inferno is attached to the airframe by just a few specially machined mounting points. If these pins exceed their microscopic fatigue limit and snap, while pulling 9G, the engine will literally tear through the fuselage and leave the aircraft in milliseconds. The pilot wouldn't even have time to pull the ejection handle. Unlike other parts of the plane, engineers design these specific elements using the infinite life principle. Once manufactured, they're scanned with ultrasonic waves and X-rays. If there is an air void the size of a fraction of a millimeter, a single manufacturing defect, the part is melted down and thrown away. The tolerance is zero because that bolt isn't just holding metal, it is holding the pilot's life and the ultimate fate of the aircraft. Next time you look up and see a fighter jet soaring through the sky, don't just see an aerodynamic shape or incredible speed. See a billion-dollar war waged atom by atom against the most destructive forces in nature, against pressures that could shred metal like paper. If this engineering miracle fascinated you, click the video on screen right now, where I explain how the massive hellfire inside a jet engine doesn't just melt the engine itself. Remember, there is no magic in the modern world, just incredibly good engineering. I'll see you in the next one.